This chapter is going to cover circular motion, center of gravity, and rotational mechanics. It's going to be a long one, so sit back and get comfortable. All right, rotational motion. What we've been talking about up until now is what's called translational, where we just relocate something. We drop it off of a cliff or something. In rotational mechanics, we're going to change the orientation. We're going to spin things. All right, just some background information. Circumference is the outside of the circle. I don't think any of you actually have to write this down, I'm hoping. Circumference is the outside. Radius is from the center to the side, and diameter goes all the way across. Small circle is half the radius, half the diameter, and half the circumference, all right? So they scale proportionally. We're all two-dimensional here. I haven't hit surface area, nothing like that. All right. So let's start looking at circular motion. First thing we have to do is get some vocabulary down. Rotational speed is how many times you turn around per second. It's the revolutions per second. Tangential speed is a little different. That, if you guys remember what a tangent is, it's an imaginary line perpendicular to the surface of your circle. So if you choose a point, if I were to choose this point, the line would be this direction. It's just an imaginary line this way. So as we look at tangential speed, you can kind of think of general speed. As you think of revolutions per second, it's going to depend on where you are. If you're close to the center, you don't have to go very fast to go around once, right? But if you're way out here and you got to go all the way around once, you're going a lot faster. So it's going to depend on where you are, what your tangential speed is, right? So you have this little guy here, and he's going in a circle, and let's say this is turning, just say once every second, make our life easy. This guy's going to go around once in a second. This particular circumference of his circle, this guy's got farther to go in that second, right? They are still each have an identical rotational speed. The rotational speed is going to be 1 revolution per second because I just said so. But their tangential speed, which is very close to linear speed, but it's going to be turning here. We think of just general speed like a car, is going to be way faster for the little guy on the outside. All right, so let's take a look at two wheels hooked together and how that works. So we're going to start on the small wheel, and we're going to say this small wheel turns once. You could start on the big wheel, but for our purposes, let's just start here. This is going to turn one time. These are connected by a rope, all right? If this turns one time, the question is, well, does this turn one time? And I think pretty easily you can see the answer is no. You're going to not take up that much rope to turn this big wheel one time. So the rotational speed on this one is actually going to be less. It's not turning 1 revolution for each time this turns 1 revolution. But let's look at the tangential speed. These are attached by a rope. This rope cannot be going faster over here than it's going over here. It's all attached in one big rope. So the tangential speed on the rim, where the rope is, notice that little addition has to be on the rim, is going to be the same no matter where you are. So this is going to have a greater rotational speed, but they're going to have identical tangential speeds. All right, let's look at inertia, and let's go back to plain old inertia for regular motion. A gold brick is much more difficult to move. It has more mass. A normal brick or a styrofoam brick is easier to move. It has less mass, all right? Pretty simple. Well, that's also true for what's called rotational inertia. Something that's very, very heavy with lots of mass is going to be harder to rotate than something that's plastic and easy to rotate, all right? And this is no big deal. We've all experienced this, right? Easier to flip a pee-wee bat through the air and have it swing end over end than a heavier bat. All right, so rotational inertia, what's it going to depend on? It's going to depend on the total mass of the object and it's going to depend on where that mass is located. So the farther out it is, the greater the inertia. The closer to the center, the less the inertia. Okay? So when you look at the mass, the farther it is from the axis of rotation, right, the larger the rotational inertia, the harder it is to turn it. So if you're going to spin something and it's the mass is located on the outside, it's actually harder to rotate it than if the mass is all together in one tight little ball. All right, so there's a formula, and that is it's the rotational inertia is equal to the mass times the distance squared. All right, and that distance is of the mass. So the farther out that mass is, and obviously we have to add up all the masses if it's going to be spread out, but the farther out the mass is, the greater the rotational inertia. All right, so I just said it. The farther out the mass is, the greater the rotational inertia. So if you have somebody spinning and they have all their mass as close to themselves as they can hold it, a tight little ball, right? Their rotational inertia is less. If they throw a leg or an arm out, all of a sudden they've increased their rotational inertia. All right, let's look at which one's easier to balance. And this one is not intuitive at all. This is not intuitive, but I don't know if you should try it with a hammer, but you can certainly try it with something heavier at the top. The odd answer is B is easier to balance because it has a greater rotational inertia. It actually doesn't want to rotate as much. A, all the mass is by your finger. It wants to rotate quite easily. The Exploratorium has a great demonstration of this, but you can do it at home. Just, again, maybe not a metal hammer over a tile floor or something like that. Okay, let's look at legs. The reason when you sprint, you got to bend your legs. People who shuffle don't actually go as fast as people who will bend their knees. And it has everything to do with rotational inertia. It is also why animals with long legs tend to have slower strides. It's harder to move that long leg than it is to move that short leg. And again, that's one reason why when you're running, you bend your knees, is that will reduce your rotational inertia on your legs. Okay, take a look carefully at these two discs, I guess is what I want to call them. All the mass on the one on the left is towards the center, and then all the mass on the one on the right is towards the outside. All right, so as you roll them down the ramp, which one's going to be easier to roll, right? Which one's going to be harder to roll? Which one has greater rotational inertia is going to be the one that's harder to roll is the one with all the mass on the outside, and the one that's easier to roll is the one that has all the mass on the inside. So the one on the left side is going to be the winner of the race, and the other one's going to be the loser. This is the exact same thing as I just said on the previous one, but I wanted to do it again just for fun. So you have two rings. One's made of wood, one's made of metal. Say they have the exact same mass, total mass, because obviously the metal one is hollow, the wood one is solid, but their total mass is the same, but the mass distribution is such that the metal one has all the mass on the outside, and the wood one has some of the mass on the inside. That means the wood one's going to be easier to turn. It's going to get a greater velocity. It's easier for it to turn because it has at least some of its mass on the inside. All right, torque. When we look at torque, we're going to look at two things. You're going to look at the force you apply to a lever arm and the length of that lever arm. The force you apply has to be perpendicular to the lever arm, right? So if you're pushing down on a wrench, and if you're pushing straight down, all of the force you are applying will be translated into torque. If you're pushing at an angle, then only some part, and we'll have to do vector analysis for that, and won't that be fun, but only some part would be coming straight down onto your lever arm and would be changed into torque. So when we look at torque, the important thing is going to be the force applied that's perpendicular straight onto your lever arm, and how long is your lever arm. All right, so let's look at this on the left side, remember I said we'd have to do some lovely vector analysis if you didn't apply your force perpendicular. So only the amount of force that is perpendicular to the lever arm counts. And so one way to kind of calculate that is to imaginarily turn your lever arm this way and then see the amount of force applied. The other way to do that is just to do the it would be the adjacent side. So the cosine of this angle here would give you the amount of force applied down. All right, so if you are going to be efficient, you're going to apply your force exactly perpendicular. That's the best way to do it. If you want even more torque, you get a longer lever arm because they're multiplied, right? So the longer the lever arm, you're going to increase your torque without having to increase your force. Okay. And you don't need to write any of this down. This was sort of just for fun, but the torque of a pirouette, you're going to get more rotation if your feet are farther apart. All right, and that's some of the reason of the dance moves. The reason to move your feet far apart is it essentially increases an imaginary lever arm. You don't need to write any of this down either. I'm assuming you know this, but when you're biking, you get more torque when your lever arm, when you're perpendicular to your lever arm, which is when your pedal's out front. When it's right over that axis, you're not really applying any force to move the bike forward. All right. Now we have to balance torques. And again, this is very much like my favorite toy, but this time we're not worried about mechanical advantage. What we're worried about here is making sure that these are balanced. And so that's a simple equation. Your force down has to equal the lever arm. And then again, the force down has to equal this lever arm. So you just set those two equal if you're not going to have rotation. If one of them is off, then you're going to have rotation. This can be true any which way you do that. All right, we're also going to do center of mass and center of gravity. And this is a little technical, but the average position of the mass in an object is the center of mass. And hey, here on Earth, where we have constant gravity and equal distribution of gravity, we can call it the center of gravity, and we can be talking about the exact same thing. And we don't need to be super picky. I think if you go work for NASA, you might have to worry about the difference. But for the rest of us, these are going to be pretty much interchangeable. All right, so locating the center of gravity, sometimes it's the very center of something. You know, it can be. It doesn't have to be. The very center of a donut is empty space, and it's the center of its gravity. So sometimes it's simple and sometimes it's more complicated. If you have one part that's more dense, it's going to be obviously leaning that direction. All right. For stability, what I mean by that is, are you going to fall over or not? All right. If your center of gravity is anywhere over your base, you're not going to fall over. If the center of gravity is shifted so that it's no longer over your base, you're going to fall over. That's pretty simple. All right, so 3 trucks, and the question is, which one is gonna tip over? And I don't know what they're carrying. This guy's carrying a liquid in what looks to be like a regular tractor trailer. Don't ask me why. Here you got a standard tractor trailer where the center of gravity is just in the middle. Isn't that nice? This guy is carrying, I don't know, an upside down piano, it looks like. And the center of gravity is way up here. Isn't that awesome? Well, let's look at them one at a time. Center of gravity way up here, drop it down. Ooh, look, he's safe. It's in his base. Center of gravity is in the middle. He's safe. It's in his base. The center of gravity is low. That seems like a good idea, but it's drastically shifted off to the left, which makes it a bad idea because, look, that's outside of the base. This is the tractor trailer that tips over. All right. Balance beam, you don't have to write any of this down, but the reason we put our arms out is to increase your rotational inertia. It's also why those tightrope walkers have that really long stick. I'm sure there's a name for it. I don't know what it is, but the reason they hold that is a really long stick. That mass is very far out. It has great rotational inertia, and it can stabilize them. Oh, yay, centripetal force. All right, centripetal force. So centripetal force is, it literally means center seeking or towards the center. It is a true force because you have to apply centripetal force. So let's look at a car going around a curve. All right, here we go. Cars going around a curve. Well, what makes it not go straight, right? Cars, and we know, Newton's laws, things are just going to keep going forever, right? They go straight. If we turn it, there must be a force acting on it. And in this case, it's probably the road and some friction. Maybe the road is banked and it's the normal force. I don't know. There is some force acting on it this way that's going to make this car turn. All right? And that's called the centripetal force, or think center-seeking force. It takes it towards the center. It is a real, true force applied to an object. All right, so we have a string and a cup, and we can put a bug in the cup, we can put water in the cup. I don't care what we put in the cup, we're going to twirl this cup around. And the question is, what force is acting on this cup? And it's turning like this in a circle all the way around. And so as we look at this, which way would the cup normally fly? I mean, I guess I think of it going this direction in general. Maybe it's coming this way, I don't know. It's going to go straight if it doesn't have the string. If that string snaps and it's moving, it's just going to fly off, right? Straight line. That's not what's going to happen if we have a string attached. The string is going to apply a force this direction. So the force being applied is towards the hand. Again, towards the center, and it's going to cause it to rotate. All right, there we go. We have A is your centripetal force. B is the path that it's taken with the string. C is going to be the path it would take without the string, and D is going to be an imaginary force that we're going to get to in a minute. It is not a real thing. All right, let's look at centripetal force examples. So for this car going around the curve, it's the force of friction holding it, causing it to turn. Force of friction is going to be the pink arrow. Does it have to be the force of friction? No, we can bank that curve high enough and well enough that you could actually have no friction and you could get that sucker to turn, but that requires some really nice vector analysis. So let's just start with force of friction right now is causing it to turn in. Okay? Tension of the string causing it to turn in. That's also centripetal force. Okay? Gravity on Earth, centripetal force. It's just gravity. Gravity, again, center seeking, causes something to come towards the Earth. All right? So if I were to throw a ball into a ring, right, and have it turn, the only force acting on it is the force of the ball against the ring, the normal force in this case. And the question becomes, what happens when the ball hits the outside? So here we go, it's coming in. This is pushing on it towards the center. It can't go straight. It can't escape here because of the metal ring. So it gets turned in. That's a normal force being applied by this ring, right? It's just not allowing it to escape. But when it hits here, it just goes straight. Sometimes people think it like turns this way or something. It doesn't. It just goes straight. It just goes exactly straight. There's nothing acting on it anymore. Air resistance and all that. But remember the imaginary world we live in physics class. Okay. So what's the magnitude of your centripetal force? Well, it depends on a couple things. The faster the speed, the greater the centripetal force. You can imagine that by just imagining a ball on the end of the rope and you're spinning it around. The faster you spin it, the more you can feel the tug on that rope. All right? If the radius is small, you have more centripetal force. If the mass is large, put a bowling ball on the end of that thing, you'll feel a greater force, I guarantee it. All right. Most of you can please just completely ignore this slide. All I want to show you is that, remember that velocity is a vector. And when we look at acceleration, we can be looking at just the change in direction of velocity. That's all we're looking at here is the change in direction of our velocity. We're not talking about an increase in speed. We're simply talking about the fact that the velocity, it was going, one direction, and we've pulled it down to go in another direction. Both of these are getting pulled down. So you're going to be able to calculate the change in velocity. And I don't want you to worry too much about that. I just want you to remember that we're not actually speeding these things up. We're changing the velocity direction. All right, so here we go. Look at this fun equation. And yes, you need little hearts and stars by this one. This is the force. Excuse me. All right, your rotational force is going to be determined by the mass of the object times its acceleration. And we just saw on the previous slide that we can substitute acceleration. We can put v squared over r. All right, and that's how we're going to find our force. When we talk about our rotational stuff, we're going to look at the mass of the object, the velocity squared over the radius. All right. All right, let's look at a ball being released. And as long as let's look at the perfect world. If you release that ball anywhere above this line, it should, by conservation of energy, make it around the loop-de-loop, right? We don't live in that world. You want to release it up, obviously, a little higher. And as long as that velocity as it goes down over r squared is greater than mg, right? mg here, mass times gravity, pulling it down. As long as our velocity is greater than that, it will not fall off the loop. All right, remember that imaginary force we talked about? It is not what I would consider a true force, but it's a force that you could feel depending on the system you choose. So if we're spinning a can and you have a ladybug in it, we know that the ladybug wants to go straight, right? Wants to, but left alone, all things inertia would go in a straight line. But that string is causing it to turn. Well, if you were to change your point of view and just imagine that you're the ladybug and your whole universe is a can, and yeah, I think this starts to get weird, but whatever. If the whole universe is a can, what the bug feels is what's called a centrifugal force. It is an apparent force. It is not going to be called a real force. It's an apparent force caused by the inertia of the bug wanting to go straight, the normal force of the can. But we can see from the outside world what's actually happening. But if you were to get rid of that and just look at what the insect feels, it would feel it as what's called the centrifugal force. All right, simulated gravity, yes. Oh, and if you want to watch just a weird movie, do 2001: A Space Odyssey. The end is just bizarre. But if you spin something, right, people are going to get spun to the outside, and we're going to do a little math with just for fun. But when you're spinning something, the basic effect of that person wanting to go straight and the normal force is going to cause what's called simulated gravity. You're going to feel as if you're standing on Earth if you spin it fast enough with the right radius. All right. Let's look at momentum. We have plain old linear momentum that we remember, mass times velocity. We remember momentum. And then you have angular momentum. And for that, for your angular momentum, you have the rotational inertia, right? That's how far out your mass is and how much that mass is out there and the distance it is out, what we already covered. And you have how quickly something's rotating, okay? So what's that rotational velocity? So just like in regular momentum, you have mass times velocity. In angular momentum, you essentially have mass times velocity. The inertia is caused by the mass and the distribution of that mass. And then you have the rotational velocity. So let's look at this in practice. Here we go in practice. We have to preserve angular momentum, right? So if you have a skater on ice and there's nothing acting on her as she spins, minimal stuff acting on her, right? Let's take away friction of her skate. She's not going to put her skate out and stop herself. As she spins, she can increase her velocity by decreasing her rotational inertia. How do you decrease your rotational inertia? Is you make yourself more in line, right? You take your arms into a little tight ball or up. As long as they're close to the axis of rotation, you've decreased your rotational inertia. You will speed up your velocity. And then you don't have to do anything if you want to slow down except for put your arm or a leg out or something out. And that rotational inertia instantly increases, and that instantly decreases your velocity. You don't need friction here. You don't need the ice applying a force to you. That is simply going to slow down your velocity because the momentum is what is conserved. Remember, conservation of momentum. That is true for angular momentum as well. So this, exactly what we just saw with the skater. Okay, same exact slide. A large inertia by putting your arms out or a leg or something. Smaller inertia by holding everything tight, and you get a faster rotation. And that's the same formula on the bottom, just a reminder. Okay, so if we're going to have conservation of angular momentum, if we hold a wheel or a disc that's spinning, and it has to be fairly heavy for this to work. But you can be sitting on one of those chairs that spin, and if you're holding a fairly heavy wheel or disc, bicycle tires usually good enough to do this. And again, this is at the Academy of Science. If you hold it, you can actually get yourself to spin the other direction because the overall momentum of the system has to remain zero. Okay, and so if you flip it, right, you're going to change your rotation. So in the previous slide, he was holding that little disc down, and then he flipped it. Okay, when we look at a helicopter, similar idea, you have the blades spinning one way, the body would just spin the other way, and that just would be bad, and they would all crash and die. It would be horrible. The way to solve that problem is to have the little tail, blades, rudder, I don't know what that little tail one's called, but the point of it is that it applies a force to balance out the desire of that lower body to spin opposite of the blades. Rotor, there you go, smaller rotor on the tail exerts the torque to balance out the desire of the body to rotate. Last slide, just for fun. Not really, it's so you can have practice doing this. But if we wanted to figure out simulated gravity, remember I said we would pretend that we're going to figure out simulated gravity just for fun. We know that regular gravity, the force of gravity, is mass times gravity, mg. And what we're going to try to simulate it with, the centripetal force, is mv squared over r. So we can just set these two equal to each other and figure out, how fast we have to spin this thing. The first thing we'll see is that, just like in energy, the masses cancel. Isn't that a beautiful thing? You're going to find that, again, a couple times in this unit, that you can actually just get rid of the mass. And you're going to be left with v squared over r equals gravity. So if you want to find out gravity, remember, is going to be 9.8. But you can just use this little short formula if I ask you to find simulated gravity versus trying to work out this big, well, it's not super long, but this slightly longer one. And there are a couple questions that are going to ask you, how big of the radius do you need? How big to, equal Earth's gravity? And so you can solve for r, how fast does it have to spin? Well, you can solve for velocity, and gravity should be 9.8 unless I decide to put you on Saturn or Jupiter.